Good day, this is Basic Calculus, topic continuity. So throughout this video, we will discuss continuity of a function at a point, continuity of a function at an interval, and continuity of a function for all real numbers. Now let's have first continuity of a function at a point. So let's have example 1. Is the graph of f of x equals 3x minus 1 continuous at x equals 1? Now since we are given the graph of f of x equals 3x minus 1, then it's easier for us to identify whether the function is continuous at x equals 1. Okay, so we have here x equals 1. So at x equals 1 on the graph, we can see that we did not encounter any hole. There is no break. There is no jump in the graph at x equals 1. At the same time, tracing the graph from the left going to the right of x equals 1, we did not lift our pens. Therefore, we can say that f of x equals 3x minus 1 is continuous at x equals 1. Next, example 2. Now, is the graph of the rational function f of x equals 3x squared minus 4x plus 1 all over x minus 1 continuous at x equals 1? So again, we are given the graph of our function. That is the graph. Now, the question is the graph continuous at x equals 1? Now, looking at the graph, at a glance, we can see that at x equals 1, there is a hole in the graph. Again, at x equals 1 on the graph, we encountered a hole, meaning to say the function is not continuous or discontinuous at x equals 1. Now, this kind of discontinuity is called removable discontinuity. Now, let's have example 3. Is the graph of f of x equals 1 over x continuous at x equals 0? Now, we can see here in our graph that f of x equals 1 over x has vertical and horizontal asymptotes. Okay? At a glance, we can see that x equals 0 is the vertical asymptote of our graph. Tracing the graph from the left of 0, as our x approaches 0, from the left, we can see that our graph moves downward indefinitely. On the same manner, when we trace the graph, as x approaches 0 from the right, we can see that our graph also is moving upward indefinitely. Okay, so our graph will never touch x equals 0, since x equals 0 is a vertical asymptote of our graph. Meaning to say, the graph of f of x equals 1 over x is discontinuous at x equals 0. Now, this kind of discontinuity is called non-removable or essential discontinuity. Let's have here. Okay, now let's have function f of x. Now this is the graph of our function. Now we can see at first glance that x equals 0 is the vertical asymptote of our graph. Now let's determine if f of x is continuous at the following points. Now at x equals -4. So looking at the graph, we have here at x equals -4. On the graph, we did not encounter any hole, meaning to say at x equals -4, f of x is continuous. Next, we have at x equals -2. Alright, -2 is here, and on the graph, we encountered a hole at x equals -2. So meaning to say f of x is not continuous at x equals -2. Now let's have at x equals -1. So at x equals -1, on the graph here, okay, there's no hole, there's no break, meaning to say at x equals -1, f of x is continuous. Now at x equals 0, at x equals 0, that is the vertical asymptote of our graph, meaning to say our graph will never touch x equals 0, meaning to say f of x is not continuous at x equals 0. And lastly, we have x equals -3. X equals 3. So at x equals 3, alright, it's there. There's no hole. There's no break on the graph, meaning to say at x equals 3, f of x is continuous. Now let's have example 4. Determine if f of x equals x cubed plus x squared minus 2 is continuous or not at x equals 1 without illustrating its graph. Okay, so without its graph, to check if the function is continuous at x equals 1, then let's check the 3 conditions of continuity. So the first condition is that f of c should exist. So here, the first condition now, or let's just have it as A for the first condition, f of c should exist. So here, since our x is equal to 1, then we will look for f of 1. So f of 1, okay, plugging in 1 to our function. So we have 1 cubed plus 1 squared minus 2. So that's 1 plus 1 minus 2. That's 0. Meaning to say f of 1 exists. So first condition is satisfied. Next, let's go to the second condition. The second condition is that the limit of f of x as x approaches c should exist. Now here our x is 1, so we have the limit of f of x as x approaches 1 should exist. So here we have the limit of x cubed plus x squared minus 2 as x approaches 1. Right? Now, since we are given a polynomial function, then we can have the limit through substitution method. So you have here x equals 1. So you have here 1 cubed plus 1 squared minus 2, and that is 0. So the limit of f of x as x approaches 1 is equal to 0. Therefore, the limit exists, so the second condition is met. Okay, now checking condition 3. So condition 3 states that f of c should be equal to the limit of f of x as x approaches c. Now in this example, f of 1 is equal to the limit of f of x as x approaches 1, because f of 1 is 0 and the limit of f of x as x approaches 1 is also equal to 0. So our third condition is satisfied, meaning to say f of x equals x cubed plus x squared minus 2 is continuous at x equals 1, right? Okay, next. Let's have example 5. Now, is the function f of x equals x plus 1 when x is less than 2 and 2x minus 1 when x is greater than or equal to 2 continuous at x equals 2? Here in this example, we are given a piecewise function. Okay? Now let's solve. Let's try to see if the piecewise function is continuous at x equals 2. So let's check the conditions of continuity. So we have, okay, first condition, let's solve for f of 2. Okay, now take note that we are given here a piecewise function. Okay, so you have to be very careful which piece of the function you will use to evaluate f of 2. Now here, we have x plus 1 when x is less than 2, and 2x minus 1 when x is greater than or equal to 2. So since we have here f of 2, then we will take the piece of the function that will satisfy for x equals 2. And that piece of the function is 2x minus 1. So in evaluating f of 2, we will use 2x minus 1. So we have f of 2, it's equal to 2x. Okay, let's write na lang. 2x minus 1. That's basically equal to 2 times 2 minus 1. That's 2 times 2, 4, minus 1 is 3. So f of 2 is 3. Okay? Next. Check the limit of f of x as x approaches 2. Okay? So, alright, since we have here a piecewise function, then it's wise to find the limit of the function from both sides to start first with the left-hand limit. Okay, so let's have first the left-hand limit. The limit of f of x as x approaches 2 from the left. So we have here. Now, going back to your piecewise function, you need to also be careful with the piece of function that you will use to evaluate or to find the left-hand limit. Okay, now since we are looking for the left-hand limit or the values of x are approaching 2 from the left, so these are the values of x that are less than 2. So for the left-hand limit, for evaluating the left-hand limit, then we will have to make use of the piece of the function that is x plus 1. Okay, so we have here, okay, the limit of x plus 1 as x approaches 2 from the left. Okay, we can now use direct substitution. So you have here 2 plus 1. So the left-hand limit of our function is 3. Okay, now let's have now the right-hand limit. So let's solve for the limit of f of x as x approaches 2 from the right. That's equal to the limit. Now, the values of x that are approaching 2 from the right are the values greater than 2. So we will use the piece of the function 2x minus 1 to evaluate the right-hand limit of the function. So you have the limit of 2x minus 1 as x approaches 2, okay, from the right. Direct substitution. So you have 2 times 2 minus 1. 2 times 2 is 4, minus 1 is 3. Now we learned previously that when the left-hand limits and right-hand limits are equal, then the limit from both sides exists. So, going back to our second condition, the limit of f of x as x approaches 2 from both sides is equal to 3. Okay? Now, checking condition C, f of 2 should be equal to the limit of f of x as x approaches 2. And we can really see here that f of 2 is 3, and the limit of f of x as x approaches 2 is also equal to 3. They are equal, meaning to say f of x is continuous at x equals 2. Alright? Next, example 6. Here, now is the function f of x, okay, still a piecewise function, okay, x plus 1 when x is less than 2, and 2x minus 1 when x is greater than 2, continuous at x equals 2. Now, checking the first condition, we have f of 2. Okay, now looking at our piecewise function, we only have pieces of the function that is true for x less than 2 and for x greater than 2. There is no piece of the function that is true for x equals 2, meaning to say f of 2 does not exist. Okay, so since the function failed at the first condition, we do not have to check the two remaining conditions further. With this, we say that f of x is not continuous at x equals 2. Okay, now we have here function. Let's have that as f of x. Okay, now let's check, given the graph of f of x, if the function is continuous at x equals 0. Okay, now let's have the first condition. Let's look for f of 0. So f of 0 based on the graph is at 1. So f of 0 is equal to 1. Okay, next, the limit of f of x as x approaches 0. Now, since we have the graph, okay, we can easily identify the limit. Let's have first the limit of f of x as x approaches 0 from the left. So, tracing the graph, as x approaches 0 from the left, we can see that our f of x is approaching 0. So, our left-hand limit is 0. Okay? Similarly, tracing the graph, okay, as x approaches 0 from the right, we can see that our f of x also is approaching 0, meaning to say our right-hand limit is equal to 0. Since our left-hand limits and right-hand limits are equal, then the limit of f of x as x approaches 0 from both sides is equal to 0. Okay, so the second condition is also satisfied. However, when we go to the third condition, f of 0, which is 1, is not equal to the limit of f of x as x approaches 0. So our function failed at the third condition. This means f of x is discontinuous at x equals 0. Next, we have here a piecewise function. Okay, now checking the three conditions of continuity. Is the function continuous at x equals 1? So we have here f of 1. Okay, f of 1 is filled in that. So f of 1 is equal to 1. Okay. Now, the limit of f of x as x approaches 1. Okay, checking the left-hand limit, we can see that as x approaches 1 from the left, we can see that our f of x is also approaching 3. So our left-hand limit is 3. Checking the right-hand limit of the function using the graph, tracing the graph. Okay, as x approaches 1 from the right, we can see that our f of x is approaching 1. So our right-hand limit is 1. Since our left-hand limits and right-hand limits are not equal, then the limit of the function as x approaches 1 does not exist. Since the function failed at the second condition, then f of x is discontinuous at x equals 1. Right? Now let's go to continuity of a function on an interval. Now let's review first interval notation. We write the beginning and ending numbers of an interval and use a square bracket when we want to include the extreme values, or a round bracket when we don't want to include the extreme values. So for example, we have here a closed interval from -1 to 1. This means our extreme values that are -1 and 1 are included. Okay? For example B, we have here an open interval of -2 to 0. Since this is an open interval, so our extreme values that are -2 and 0 are not included. We also have here a closed and open interval. So you have here 0 to 4. Since 0 is having here a square bracket, so 0 is included and 4 is not included. Now let's go to the seventh example. Consider the graph of the function below. So we have here f of x equals 3x minus 1. Now using the given graph, determine if the function is continuous on the following intervals. So we have here a closed interval from -1 to 1. Now tracing the graph, okay, -1 on the graph, we have here tracing the graph from -1 -1 to 1. Alright, on that interval, we did not encounter any hole, any break, any asymptote. So meaning to say, at the closed interval -1 to 1, the function is continuous. Next, let's have the open interval from -infinity to 0. So since we are starting from -infinity, so we can have here. So from -infinity, tracing the graph from -infinity going to 0. Alright, we did not encounter any hole, meaning to say at the interval, the graph is continuous. Right? Next, going to the third, we have the open interval of 0 to positive infinity. So tracing the graph from 0 here to positive infinity, we also did not encounter any hole, meaning to say at the interval of 0 to positive infinity, the graph is continuous. Now let's go to example 8. Using the given graph, determine if the function is continuous on the following intervals. So we have here the graph of f of x equals 3x squared minus 4x plus 1 all over x minus 1. Now let's try to check if on the interval -1 to 1 inclusive is our function continuous. Okay, so let's have first, okay, let's trace the interval. Okay, from x equals -1 on the graph we have here. So tracing the graph going to x equals 1. Alright, we see here that at x equals 1, we have a hole on the graph. Now, in our interval, 1 is included because we used here a square bracket. So since the graph has a hole at x equals 1, then the function is not continuous on this interval. Again, why? Because 1 here is included in the interval. Next, let's have B. Okay, let's have B. Okay, we have the open interval from -infinity to 0. So tracing the graph from -infinity going to 0. Okay, let's do it properly. Okay, from -infinity going to 0. There, we did not encounter any hole. So meaning to say on that interval, the function is continuous. Right? Next, let's go to the next interval from 0 to positive infinity. So tracing the graph, okay, let's use another color. Right, tracing the graph from 0 to positive infinity. So from x equals 0, we have there. Okay, going to positive infinity. Alright, we encountered a hole at x equals 1. Since we encountered a hole at x equals 1, meaning to say at the interval 0 to positive infinity, the function is not continuous. Right? Now let's have, okay, an additional interval. Let's have the interval of, okay, 0 going to, okay, 1. So let's have the open interval of 0 to 1. Okay? Now from tracing the graph from x equals 0, so we'll start over here. Going to 1 to x, okay, going to 1. Alright, there. Now, remember that in our example given letter D, 1 here, we have here an open interval, meaning to say our extreme values are not included. So here 1 is not included. So since 1 here is not included, then the hole in the graph is not included in the interval. Okay? Meaning, at the open interval of 0 to 1, the graph is continuous. Right? So that's it. Let's have here example 9. Find the interval with which this function is continuous. We have here f of x equals x plus 2 over x squared minus 3x minus 10. Okay, we have here a rational function. So solving, we have f of x is equal to x plus 2 all over x squared minus 3x minus 10. So to find the points of discontinuity and the point of discontinuity and the vertical asymptote, let's factor out our denominator. So we're able to find the factors that are x plus 2 times x minus 5 as factors of x squared minus 3x minus 10. Okay, dividing out common factors. So we are left with 1 minus 1 over x minus 5. So to solve for point of discontinuity, we'll take x plus 2 equals 0. Solving for x, we have x equals negative 2. So that is where our removable discontinuity is. So we know that there is a hole at x equals negative 2 in our graph. And solving for the vertical asymptote, we'll take x minus 5. So x minus 5 equals 0. X equals 5. So that's the non-removable discontinuity, right? Having the graph of our function, so we can really see that there is a hole at x equals negative 2 and x equals 5 is indeed the vertical asymptote of our graph. So writing the interval with which the function is continuous, we will make use of the open interval from negative infinity to negative 2. We will use open interval because we will not include negative 2 there because there is a whole negative 2. And union from negative open interval negative 2 to 5, union the open interval from 5 to positive infinity. Right? Now, what makes a function continuous for all real numbers? So, all you have to do is inspect the entire graph. There must be no break in the graph, no hole or jumps. Okay? So, for example, we have here, okay, f of x. Inspecting f of x. Okay, from left to right. There's no hole, no break on the graph, meaning to say f of x is continuous for all real numbers. Right? Next, let's have here, okay, let's have that as, okay, g of x. Now tracing g of x from left to right. Okay, we encountered a hole at x equals 0. So meaning to say the g of x is discontinuous at x equals 0. So g of x is not continuous for all real numbers. Okay, so that's all. That's how to basically find or determine whether a function is continuous at a point, at an interval, and for all real numbers. Okay, so thank you and see you in our next video.